So hello, everyone, and welcome. Welcome to our summer school workshop on quantum horizons, developments, and opportunities. And it is my tremendous pleasure to let you know that we have a very special speakers, indeed two speakers. First one is Turkish-American physicist and world-class expert in the field, Professor Nuh Gedik from Massachusetts Institute of Technology. Nuh Gedik received his BS in physics from Boğaziçi University and his PhD in physics from University of California, Berkeley. He's a full professor at the physics department of MIT. Professor Gedik's research centers on investigating quantum materials by using advanced optical and electron-based spectroscopies. He has kindly agreed to join us for this school and is going to give a great talk under the title, Capturing Light-Induced Phase Transitions with Femtosecond Movies. With this, I want to thank once again Professor Nuh Gedik and invite him to begin his talk. Nuh Hocam, please come.
Thank you so much. So I also would like to begin by thanking Alikram Bey and all the organizers for organizing this wonderful event and inviting me. So today, what I want to do, I want to share with you some of our recent results in which we actually use light both to induce phase transitions as well as to actually make movies, femtosecond movies of phase transitions. So let me get my laser pointer. Anyways, you can see my mouse, right? Okay, good.
Yes, it's okay.
Good. So before I begin with the details of our work, I just want to zoom out a little bit. And I understand that this is a bit of a general audience, so I just would like to remind you what phase transitions are and how do we think about from our daily life. So the simplest example is, water. Water is one of the rare materials that actually can be found on Earth on all three forms, ice, water, and vapor. And there are phase transitions as you go between these phases. Now, how do we really think about it? Well, in the microscopic view, if you go to ice, there's this ordered phase where all the water molecules are nicely arranged in this hexagonal fashion in the usual ice. As you heat this thing, for example, then it becomes less ordered, goes into the liquid phase and the gas phase. Now, a bit more physical way of thinking about this is really to think about a free energy diagram. So if you can imagine some sort of a free energy as a function of thermodynamic variables like volume or temperature, all of these phases really corresponds to the minimas in this phase. So for example, you can see that in this plot, there's this global minima, but there's also this local minima as well. So, given enough time, the system will actually go to this phase. But if you increase the temperature, as you increase temperature, you can see that gradually this global minima becomes local minima, and this one becomes the new global minima. So what's going to happen is there's going to be a phase transition from this guy to this guy. Now, in this particular example, you can see that the volumes are different. So the two phases will have different densities. So this is kind of the general flavor of how we think about phase transitions. The reality is obviously more complex. I mean, this was the simple phase diagram of water, but a bit more realistic one for ice is this one right here. Ice has almost 11 different phases. There's the cubic ice, the hexagonal ice, and all kinds of different phases that appear as a function of pressure and temperature. So one way you can kind of think about this is that instead of these two minimas here, there's 11 different ones. And, depending on where you are in this phase diagram, some of them are, true global minimas. Some of them are actually are not, but they are actually local minimas. So just because something is a local minima, it doesn't mean that you actually don't realize it in nature. Some of the phases of the ice, even though they're not true global minima, they're stable, as long as 100,000 years, because this is a very deep minima, so it's very hard to get out of that minima. Okay, so this is kind of, in general, how we think about phase transitions. I'm a solid state physicist, so I think a lot about solids. So let's actually now narrow this down to solids. What kind of phases and phase transitions are there in solids? So there are different types. So one obvious one is an electronic phase transition. You can have solids that actually become superconductors at a particular transition temperature. They lose their resistivity at that temperature. There could be magnetic ones. There are some solids where all the spins align in the same direction. We call them ferromagnets, or they could be anti-ferromagnetic in this fashion. Or it could be structural, that you actually cool the sample down, and below a certain temperature, the structure of the material changes from one structure to the other structure. Now, often the case, these things are actually coupled. As the solid goes through a structural phase transition, its electronic structure also changes, or the magnetic one as well. So we begin with a very simple description of water, and we are adding more and more complexity. And now I'm ready to show you a bit more realistic phase diagram of some of the quantum materials. So here I just put two examples. One of them is high temperature superconductors, cuprates. The other one is another family of materials called manganites. Okay. Now what I'm plotting here, the behavior of the phases of this material as a function of temperature and chemical concentration. How many electrons are we adding to this material? And usually the chemical concentration is controlled by doping. So you can, if you substitute lanthanum for calcium, you add more electrons, etc. Now, the only thing that I want to point out from this phase diagram is its complexity. Look at how many different phases there are. So here's a ferromagnetic metal, anti-ferromagnetic insulator, charge ordered state. So there's the entire zoo of these phases that are in very close proximity to each other. And this is not special to this material. This is kind of a general theme for the quantum materials. So this is interesting for two aspects. One is, how do we really understand how do these phase transitions happen as I change temperature or doping? How do they actually happen? So there's the academic interest to understand these materials. And finally, technologically, it's also very interesting because these materials always sit on the verge of going through one of these phase transitions. They're very susceptible to external stimulation. So you can actually think about possibly making something, utilizing this and making something out of this. Sorry. Okay, so now this is in equilibrium. What I do, I don't work on equilibrium phase transitions. Rather, my goal is, can we use light, pulses of light, to actually induce these phase transitions? In other words, here, the thing would be, you change temperature or chemical doping, and then you go through this phase transition. Can I do the following? Can I just shine light onto this material right here and go to here? Or vice versa? Can I do this in a reproducible manner? So now the answer is going to be yes, but it's much less understood compared to the equilibrium phase transitions. There's actually more to this. One thing is to go between these equilibrium phases. The other thing, which is maybe more interesting, is, is it possible that you actually shine light into this system, and maybe what happens is that you create something completely new that does not even exist in equilibrium. So perhaps there is another axis here, which I can call light intensity. As I shine more and more intense light into this material, it is possible that you could go into a new phase that doesn't even exist in equilibrium. So it may sound crazy, but I hope to convince you that that is actually even possible, and that's one of the things that we have observed. So there are many questions to answer in this field. So one of them is, my intuition tell me that, when I put light into something, I would be dumping energy. So it's like I would be heating it. Obviously, I can take ice and I can shine light on it and I can heat it up into water. So it's kind of intuitive to go from a low temperature phase into the high temperature phase. In other words, it's intuitive to go from a symmetry broken phase to the high symmetry phase. But the question is, can the light do the opposite as well? Can you shine light into the high temperature phase and go to the low temperature phase? Or can you do this in a reproducible manner? So there are many other questions as well. For example, in the quantum materials, the reason why there are so many different phases in close proximity to each other is because there is a phase competition usually. Different phases are competing with each other as a function of some tuning parameter. So it turns out that you can actually use light to favor this phase or the other phase. Finally, I mean, our eventual goal is to do an on-demand engineering of the free energy landscape. So we want to basically tailor the light pulse to make this one favorable or the other one favorable. That's the ultimate goal. So these are the big questions, and I want to study them. But the way to go about this is, you know, I just would like to start with the simplest possible material that I can think of so that I don't complicate the thing. I just focus on a light-induced phase transition rather than the complexities of the material. So for this talk, this simple example material is going to be a charge density wave. So this is the outline of my talk. First, I just want to introduce you to the charge density waves in case there are some people who are not familiar with these. And I'll give you two examples. One of them is this material, lanthanum tritelluride. It's a charge density wave, and I will show you that I can use light to induce a new state that doesn't actually exist in equilibrium. In the second part of my talk, if I have time, I will actually show you that I can use circularly polarized light to make the charge density wave state in this material chiral. Okay, so let's actually start with charge density waves. Remember, this is our model system to study light-induced phase transitions. So what is a charge density wave? So a charge density wave is a material in which, you know, in regular solids, you know, maybe it's something is a liquid, you cool it down, it becomes a crystal. And in these charge density waves, if you cool it down further, what happens is that a superlattice develops in the material. In other words, there's a sinusoidal modulation of the atomic position. Some atoms will get closer, some atoms will get farther away. There's a sinusoidal wave that actually happens. Now, everything stays neutral. These are positively charged ions. So whenever these ions come together, there's more positive charge. But then the mobile electron density also compensates this. So the electron density would be high here, low there, etc. So in other words, there are two kinds of density waves. One of them is the sinusoidal modulation of ionic positions, and the other one is the electron density is also sinusoidally modulated in space. So this is very typical phase transition, a second order phase transition. There's the high symmetry state. This is the order parameter here. Above TC, it's 0, and below TC, you develop a finite modulation or finite modulation of the electron density, for example. So one obvious way to probe this system is to do diffraction. As you know, if you do X-ray or electron diffraction, effectively you are taking a Fourier transform. And what you would see is that because there's this new wave vector, you would actually see that there's this new peak that appears that wasn't there in the first place. So this is actually a very nice way of probing the amplitude of this order parameter, because the strength of this peak is really the strength of the modulation. There is also a gap that opens up at the electronic density of state. So if you were to probe this gap, you could also probe the electronic from the electronic side how this charge density wave develops. Okay, so now I just want to say a bit more about actually probing this modulation. I already said that diffraction can be way, but I just want to clarify this a bit more. So everybody knows that when you do diffraction, you send either X-rays or electrons. You can consider them as waves. And what happens is that each one of these atoms behave like scatterers. And these waves constructively add along certain directions. So I'm obviously describing Bragg reflection. And anytime you see a Bragg peak, that actually corresponds to a set of atomic planes like this. Now, if you start to see a new peak, that means there's this new wave vector that didn't happen, that wasn't there in the first place. So for my talk, I'm going to be using electron diffraction. And in the case of electron diffraction, we use, rather than X-rays, an electron beam, high energy electron beam, like 30 kilovolt electron beams. We send them into the crystal and we look at the diffraction. This is shown in reflection, but you can also do transmission. You can go through the sample if the sample is thin enough. So here's one example of a static electron diffraction. this is where your direct electron beam is hitting, and you see all these other peaks. This is transmission. So you can actually label them. Each one of them corresponds to one set of atomic planes. So this is 0, 0, 1, etc. So what do you actually learn from this picture? The intensity of these spots basically tell you the degree of order. The position tells you the distance between these atomic planes, and the width of these Bragg spots basically tells you the size of the ordered domains. I mean, if it could, you know, if the entire sample is ordered, then these would be very narrow, sharp peaks. Okay, so now we're going to use this to probe charge density waves. That's going to be our probe. And I just first, before I show you the ultra fast version of this, let me actually try to convince you that this is a very good probe of charge density wave. So here is an electron diffraction study on a charge density wave, niobium tetrateluride. And you can see that there is a bright peak here. That's the Bragg peaks, okay? And in between the Bragg peaks, you can see these tiny peaks, all right? And they show up below TC. Now, these peaks are there because this extra modulation in the charge density wave develops below TC, right? So as you cool this material down, it would be fun to actually watch that this peak is coming up because this new order is coming up. Now, here's another study from X-rays. This is a different charge density wave. And now we are looking at one of these satellite peaks. You can see that above the transition, which is somewhere around 200 Kelvin, there's no sign of this peak. This is the intensity of this peak as a function of momentum. And right at TC, this peak starts to show up. And then you can see that it goes through a very phase transition-like behavior, that it shows up at TC and the intensity increases. So the reason I'm showing you this, I would like to make the point that this diffraction is a very nice way of probing this ordered state of matter, directly probing the amplitude of the order parameter. So now we go back to our real goal. What I really want to do, I don't want to just heat up the system. People have done this for a while now. What I want to do instead, I want to go into the low temperature phase. I want to use an ultra short pulse to kick this and melt it, and then watch in real time as this order melts and reforms. My goal is to try to understand, is this the same thing as just temperature-induced phase transition, or is it different? Or maybe one step further, could I discover some new phases that actually does not happen in thermal equilibrium? So the way we're going to do this, we will use this pump probe technique, in which I have a laser, and then I split the laser into two. One part I bring and induce this phase transition on the charge density wave. The other part of the laser, I won't go into details, but I use it to actually shine it onto a thin piece of metal, and I extract electrons. And after I accelerate these electrons, I can do diffraction with these electrons. So the nice thing about this is I can control the time difference between electrons and the light by just making one of the paths longer or shorter. And that way, by taking snapshots at different time delays, I can basically make a movie. I can take the diffraction before I kick with the light, at exactly the same time the light pulse arrives, or later. And when you put all these together and you run this, you literally see a movie. Now, normally, we don't have cameras that can go into femtoseconds or picoseconds. That's just way too fast time scale. But the good thing here is that this time scale is just controlled by how precisely can you move the mirrors, and we can do this nanometer precision. So it's very easy to actually get femtosecond time resolution with these movies. So let's actually just jump into our first example. I want to look at this charge density wave, lanthanum tritelluride. And first, I just want to introduce this material to you and tell you what's exciting about this. Before that, I just want to show who did the work. So the real heroes of this work are two of my previous people, Alfred Zong, who's now a Miller postdoctoral fellow at Berkeley, and then my postdoc, Ansul Kogar, used to be a postdoc in my group. He's now a professor at UCLA. And the samples were obtained from Ian Fisher from Stanford, and many other people contributed to this work. So I told you that I was going to talk about lanthanum tritellurides. This is actually a member of this broader family, rare earth tritellurides. So rare earths are this row of periodic table. When these elements make a compound with tellurium, it becomes in this form, rare earth tritelluride. So it could be lanthanum tritelluride, it could be cerium, neodymium, etc. Now, all of these materials, you can actually make a phase diagram. They go through this charge density wave transition. So here, are different rare earths, depending on how light or how heavy they are. You can see that this is the temperature above which they are, they don't have a charge density wave, but when you cool this material below, then actually a modulation, sinusoidal modulation develops in the C direction. So the crystal structure looks like this. The charge density wave develops in the C direction, like here. Now, for some of the other materials, like these guys here, there's a secondary charge density wave that happens in the A direction. So first it goes through, it becomes like this stripe pattern where the charge density is modulated in the C direction. But if you go through the second one, there is an additional phase transition. Another charge density wave forms in the A direction. So it looks like a checkerboard. Now, the material that I'm going to be talking about is lanthanum tritelluride. And you can see that it's far on this side. And lanthanum tritelluride does not have A-axis charge density wave. It just has the C-axis one. It just becomes a stripe. And all the temperatures that people studied this, there's never an A-axis charge density wave that forms. Now, another thing you can actually see in this phase diagram is that the two charge density waves, the C-axis and A-axis charge density wave, they're competing with each other, because as the transition temperature of one of them becomes lower, the transition temperature of the other one is actually becoming higher. So this and this is competing. These two phases are competing with each other. So let's do our experiment. Let's take this material, plug it in our chamber, kick with the light, and see if we can actually observe this movie of the phase transition. So first, I just want to show you the static. So this is a static electron diffraction obtained in our chamber. Our direct electron beam is hitting here. It's too bright, so we put this ugly beam block here to block the direct electron beam. The bright spots that you see, these are our Bragg spots. So each one is corresponding to an atomic plane. We can label them. And if you can see, there's tiny spots in between the Bragg spots. And though that is there because of this extra modulation. So we have a very good handle of this order parameter of this phase. Now, what I'm going to do, I'm going to take a cut here. So you can see that there's a Bragg peak here, and there are the charge density wave satellite peaks. And there's another Bragg peak here. The one in the middle is a weakly allowed charge density wave peak. So now we're going to shine light onto this. We're going to kick with a short pulse. And I want to show you a movie of what happens after you kick with the light pulse. Now, I would like you to please pay attention to these satellite peaks. Okay, so that's actually the peaks that tells us about the order of how the charge density wave order is changing. So let's actually watch this movie. So this pattern that I'm showing is 1.3 picosecond before the light pulse kicks the sample. So let's see what happens. So you can see that the peaks are going away, right? They're almost gone. And then if you wait long enough, they recover back, right? So what did we just see? We saw in real time with femtosecond resolution, as the light pulse hits this material, it melted the charge density wave order, not the crystal. The crystal is, there. We're not melting the crystal. We're just melting this electronic order. And then if you wait long enough, about 10, 15 picoseconds, it comes back, okay? So I can actually show you a plot, okay? So what I can do now, I can sum up the intensity under the Bragg peak and also sum up the intensity under the satellite peak, and I can show them on the same plot to you. So the blue curve is the satellite peak. This is actually, if you wish, the order parameter of the charge density wave. And you can see that, it starts from 100%, and then for this laser power, it goes down all the way to 10%. So 90% decrease in the satellite peak. And if I wait long enough, it is recovering, right? In fact, I can crank up my laser intensity, and I can completely melt this state. And you can, we have data that shows this goes to 0, okay? Now, you can also look at the Bragg peak, which tells me about the lattice itself. you can see that the changes are only a few percent level, 1 or 2%, right? So I'm not doing anything drastic to the crystal. All I'm doing is I'm melting this electronic phase, if you wish. Now, there's more details here. For example, you know, the fact that the Bragg intensity goes down at longer times, it's well understood. Basically, I'm dumping heat into the crystal. As there is more heat into the crystal, the ions are vibrating more. There are more phonons around, so they actually scatter the electrons more. So there's thermal diffuse scattering. Something called a Debye-Waller factor reduces my Bragg peak intensity. So that's very well understood. And this kind of reduction is also consistent with how much heat I'm putting into the crystal. Now, what's a bit more counterintuitive is this initial increase in the Bragg intensity, right? What does the increase mean? It actually means that the lattice is somehow becoming more ordered when I first kick. When you think about it, it is actually reasonable, because what I'm doing is I'm removing this extra modulation due to the charge density wave. So the lattice itself actually initially becomes more ordered, but then the heating kicks in, so I lose intensity due to the Debye-Waller factor. So that's one thing that I can learn from the intensity, but there's actually more to this, because this is the integrated intensity, but I have the entire peak profile. I have the satellite peak as a function of momentum, so I can actually plot it. So right here, it's a very nice sharp peak, okay, telling me that the ordered, the charge density wave domains are large, right? The width was telling us the sharper the width, the longer the correlation length. Now, over here, I know that I'm losing intensity, and as you can see, the peak is much less intense, but there's one other effect that's happening. This is actually also getting broader, about 4 times broader than the initial one. This is resolution limited, this is not, right? And then if I go to the recovery, then it becomes sharper again. So another thing that we learned then, not only I am decreasing the amplitude of the order parameter, but I am also actually decreasing the correlation length. So charge density wave correlations before was maybe covering a big area, but after I kick, they are, you know, the domain size gets smaller and smaller. So there's a lot more evidence that I can tell you about, but what's basically happening is that the correlation length is decreasing. If there's a big domain here, and then over here, it looks like multiple domains in the sample. So one way to actually understand both of these observations, right now, if you wish, this is kind of my hypothesis. We have other evidence that I don't have time to go into. What's happening really here is that, to begin with, I had a nice charge density wave. I'm just showing you these sinusoidal modulations, the phase fronts of the charge density wave. Now, I kick with the light, and then it turns out that what light is doing, it puts these defects into the charge density wave. So it used to be a perfect charge density wave. Now I have these defects, right? Now, what would these defects do? So to begin with, a defect core, by definition, the order parameter here is 0, right? So the average order parameter would go down. So just like the intensity is going down. And number 2, the correlation length is kind of the mean distance between these defects. And as you have more and more defects, the correlation length will actually get smaller and smaller. So it kind of can explain both of these observations of intensity going down and the peak is getting broader. Now, we have some more evidence, but I don't want to, actually, I have some other things to show you. So I just want to move on. So far, I just showed you that I can kick with the light and I can melt this charge density wave, at least transiently. And if I wait about 10 picoseconds, 15 picoseconds, it comes back. It turns out that something a lot more interesting is also happening at the same time that actually we didn't realize after, for like a year or so. Now, let me remind you this phase diagram that in this family of these materials, there's the 2 charge density waves, C-axis charge density wave and A-axis charge density wave. They compete with each other. And in some materials, the A-axis can still, come into existence at low temperatures. But for these materials, and definitely for lanthanum tritelluride, the C-axis wins and A-axis is never realized at any temperature whatsoever, okay? So now let's see, how does this thing survive in the light-induced phase transition? So I just want to show you raw data, no analysis. So I am showing you a diffraction pattern before I kick with the light. So this is lanthanum tritelluride. here is our direct electron beam blocked, okay? And these intense spots are the Bragg spots, Bragg peaks. And these extra modulations that we see, this is the modulation coming because of the charge density wave, okay? C-axis charge density wave. Now, I want you to pay attention that there is absolutely no modulation in the A-axis direction because there is no A-axis charge density wave in this material. The only modulation is in the C-axis direction. So now what I'm going to show you is what happens to this diffraction pattern after I kick with the light. So we're going to see a before and after thing. So maybe you can actually pay attention to right here to this spot. So we see nicely the two charge density wave modulations before we kick with the light. So here's what happens after. So this is after, before, after. So hopefully you see that after you kick 1.8 picosecond, after you kick with the light, two new spots come into existence. They didn't exist before, and they never exist at any temperature, but somehow after you kick with the light, these two new spots appear. So in fact, I can show you a movie. So this is the original diffraction pattern, and I am taking this region here, and that's what it looks like 500 femtosecond before the light kicks. So if I take a cut here, you see the nice charge density wave modulations. If I take a cut in the A-axis direction, there is no charge density wave, so there's no modulation, there's no extra peaks. But let's actually watch this movie, what happens when you kick with the light. So you can see that new peaks appear in the A-axis direction, and then if you wait long enough, they disappear. So actually, I'm going to run this one more time. So you can see the peaks come in, and then they go away. So that's amazing, because what we are really doing is we are now kicking with light, and we are at least transiently realizing a phase that never exists in equilibrium, okay? So here's two frames from this movie. So this is 300 femtosecond before, and the same region I'm just mirror flipping at 1.8 picoseconds. You can see that very clearly the two new spots are here. So light is inducing a new phase. I mean, I can analyze this. I can, for example, look at the intensity of the original order by looking at the intensity of this guy, or I can look at the intensity of the new peaks. That's the red symbols here. You can see that one goes down, the other one goes up. I told you that they are competing. So what really is happening is that we are killing the one that's winning so that the other one can win. So in fact, you can also actually get some intuition from the time dependence. You can see that this is fast. The C-axis order destroyed relatively quickly, whereas the A-axis is formation of the A-axis order slow. So it kind of has to kind of wait until this guy's gone so that it can come into existence. Now the recovery is quite similar. We actually looked into the dynamics, and it's very similar. So we also see an increase in the thermal diffuse scattering, but that is quite normal as we have more phonons around. They scatter electrons, and we can subtract the spectrum. So one way to understand this is that, as I mentioned, we are putting these defects into the crystal, and at the defect cores, the C-axis order parameter goes to 0. So in other words, maybe I can show you with this picture right here. So this is our original charge density wave. So what we believe is happening is that when we kick with the light, we actually make a defect in the charge density wave. So by definition, the order parameter is 0 here, and C-axis and A-axis were competing with each other. So if you kill the C-axis order parameter here, then this other thing, A-axis order parameter, charge density wave order, can come into existence. And as these defects recover, if you wait long enough, they actually heal. As they heal, then the sample goes back to its thermodynamic ground state, the C-axis charge density wave. So this is a very nice example, I think, of directly visualizing a phase that is induced by light that doesn't exist in thermal equilibrium. So maybe this is actually a good time. Are there any questions so far? I'm gonna switch gear and talk about something else for the remaining time. Okay, doesn't sound like it. So far, I've shown you that we can kick with short pulses of light, and in femtosecond to picosecond time scale, we can induce a phase transition. It's transient, so everything recovers after if you wait long enough. But it is not destructive. So when I kick with the light, I don't actually do any damage to the sample. Everything is reproducible. Now, in the remaining 5-10 minutes of my talk, I want to show you yet another example. This is still with light, but this time everything is going to be static. So I am not going to be time resolving this. I will be shining CW, continuous wave lasers, to actually induce a new state in this other charge density wave, titanium diselenide. So before I show you this work, I also should mention who did the work. So these two postdocs, they used to be postdocs, now they are professors. My postdoc Suyang Zhu, who's now a professor at Harvard, and my colleague Pablo Herrera's postdoc Chong Ma, who's now a professor at Boston College, are the real heroes of this work. And it was in close collaboration with my colleague Pablo. So what did we do? So before I can explain this work, I would like to use an analogy from liquid crystals to motivate why it is interesting to look for a chiral phase of electrons. So, if you think about liquid crystals, you can have an isotropic phase where everything is randomly oriented, okay? Then if these things break rotation symmetry, you can also have nematic liquid crystals, okay? Now, it turns out that in quantum materials, there's the analog of this. And we have materials in which, at high temperature, the material is completely symmetric. But then if you cool it down, electrons suddenly decide that they prefer one direction over the other direction. They go through this nematic transition where, the lattice could be fourfold symmetric, but then when you cool below a certain transition, electronic wave functions are only twofold symmetric. So they prefer one axis over the other axis. So this is called nematic. So there are examples of nematic phases in quantum material. So then there's another phase in these liquid crystals where, you begin with an isotropic phase again. If you break all of these symmetries, inversion, mirror, roto-inversion symmetries, you can get this chiral phase. You can see that there's this chirality to this new phase, right? It kind of, there's handedness. It goes in right-handed or left-handed manner, right? So there's a name for this called cholesteric liquid crystals. And a long-standing question in quantum materials is, could we have the analog of this in quantum materials? Could we have chiral electronic phases, okay? Now, we all know that you could have chiral molecules, right? I mean, in chemistry, there's left-handed and right-handed version of the same molecule, but that's not what I'm really talking about. In crystals also, there could be chiral structures, right? Obviously, if the structure is chiral, the electronic wave functions will also be chiral, but that's not what I'm talking about. I'm talking about a crystal where it's achiral, all of these symmetries are preserved, but when you are cooling it below a certain transition temperature, suddenly they all decide that their low energy state is a chiral phase. So the electrons suddenly become chiral. So the question is, does this exist? Is there any material in which we actually can see this behavior? At high temperature, it's achiral, and then you cool down, it becomes chiral. So there has been some candidates. People were excited about possibly cuprates being something like this, but I don't think that is the case. But there was another suggestion, another material that was suggested that it would actually display this property. It was a charge density wave in titanium diselenide. So let me show you the crystal structure of this material. It's a layered material. Now, the green ones are selenium. This magenta thing is titanium. Now, if you look at high temperature, above the charge density wave transition, you can see that this titanium is an inversion center. This is an inversion symmetric structure. So because inversion symmetry is preserved, it's not chiral at high temperatures, okay? Now, this material does go through a phase transition. So this is what the bands look like There's 2 orbitals from selenium 4p and titanium 3d, and the vector that connects them, the material actually develops a modulation at this wave vector. And it turns out that in the beryllium zone, there are 3 inequivalent points like these. So there is actually 3 different charge density waves that are 120 degrees to each other that form. If you do X-ray diffraction, you directly see that at 200 Kelvin, a new peak appears, right? So this is a very classic charge density wave behavior. And as I said, in the plane, there are 3 directions, 120 degrees to each other, that you have 3 different modulations. Anyways, so people have been studying this material, and one of the techniques that were used in the study was scanning tunneling microscopy. So STM is a microscopy technique where you literally bring a tip, and then you record the tunneling current. As you move this in real space, you go on top of different atoms, and you record the tunneling current, dI/dV, and then you actually make a map. Okay, so this is a real space map as you move this tip around. And once you have this XY map, you can do a Fourier transform, and you can actually get the interesting modulations that are present in the sample. So what these authors discovered, they actually saw that there are 2 domains in the sample. Okay, domain number 1, domain number 2. So in both of them, they do see these 3 different charge density waves, Q1, Q2, and Q3. So the brighter spots are the Bragg peaks, right? The atomic Bragg peaks, and the spots inside are coming because there's these 3 different charge density waves, 120 degrees to each other. So the 2 domains are the following. So in domain number 1, you can see that there's Q1, there's Q2, and there's Q3. You can see that this is the most intense one, this is the medium one, and this is the weakest one, right? So there's this chirality to this. It goes from intense, less intense, and least intense. If you go to the other domain, it reverses. Then it goes the other way. Okay, so in one domain it goes right-handed. It goes in the other domain it goes left-handed. So what these authors proposed, they said that because there are these 3 different charge density waves, if you actually arrange the phases and amplitudes of these charge density waves, you can actually get a chiral charge density wave in this material. They proposed that this charge density wave is chiral. Now, there was another STM experiment about 8 years later, which actually looked into the same material, and they concluded that no, it's not chiral, it's achiral. Okay, so one STM experiment saying it's chiral, the other one is saying it's not chiral. So the question is, which one? Is it a chiral material or it's not a chiral material? So we decided to look at this system, and in order to see if this material is chiral or not chiral, it turns out that nonlinear techniques, nonlinear optical techniques are very powerful because you can actually understand if a particular symmetry is broken or not broken. They are very, very sensitive into symmetry breaking in the system. So we used in particular a technique called Photocard. Okay, so let me explain what this is. So it's very simple. We shine light into the sample, and without applying any voltage, we look at a current, a photocurrent that is flowing in the sample. So it goes like this. So we shine circularly polarized light, and we look for a current that is running in the propagation direction of the light. So the argument is this: if you shine left circularly polarized light, and then switch the polarization to the right circularly polarized light, if there is a current that actually depends on this chirality, the sample must be chiral. Okay, but let me explain why that is without going into any math. So let's imagine an experiment where I am shining circularly polarized light into a sample that's not chiral, and then let's say there's some current flowing, photocurrent flowing in this experiment. Now, if I look at the same experiment in the mirror, my left circularly polarized light becomes right circularly polarized. The object is not chiral, so it looks the same. The current also looks the same. Okay, so you can see that changing the polarization of the light to right circularly polarized light is effectively weaving the same experiment in the mirror, and the current doesn't change. So we conclude that if the object is not chiral, there should be no current that switches because you switch the helicity of the light. So you know, for an achiral object, helicity dependent current is not allowed, is not symmetry allowed. Okay. Now, instead, if you have a chiral object like your hand has a chirality. In the mirror, this would look different. Okay. And therefore, my argument here would not work. So then it is allowed that if you switch the chirality of the light from left circular to the right circular, you would actually, it would be symmetry allowed to get a current, photocurrent, that depends on the chirality. So it's very simple. If you shine light, left circle, and change the left from left circular to the right circular, if you see a change in the current, that means your object is chiral. If you don't see, then it's not chiral. So we teamed up with my friend Pablo, and you know, we did this experiment. We want to shine light through the sample, but at the same time measure the current that is flowing in the direction of the light propagation. So we need to make the sample thin enough so that the light can go through. We also need to put an electrode on the top that's thin enough to make the light go through. So we solved this problem by preparing 100 nanometer thick samples. We put a metal on the bottom, and then, you know, as an electrode, we use graphene, you know, monolayer of carbon. And then what we do is we shine light here. Light goes through. We have an electrode, so we can measure the current going through. And the experiment looks like this. We have a quarter wave plate that actually studies the current going through the sample. As we rotate this quarter wave plate, the polarization goes from left circular polarized to linear to right circular polarized, etc. Right? So our goal is to see if there's any difference between this and this. If there is, then the sample is chiral. If not, it's not chiral. So, you know, we took this material. First thing we do, we want to do a check. So we go above the phase transition, which everybody agrees is not chiral. Okay, so we go there and we do this experiment. Indeed, you know, left circular polarized light and right circular polarized light looks exactly the same. So good, it's not chiral as known. Now, the funny thing is that there is some current flowing, and that's actually also normal. There is the thermal effect where you're heating one of this electrode more than the other one. There's a temperature gradient that actually leads to a voltage gradient, and there's a current flowing, but that current doesn't depend on helicity, right? So you can just subtract as a background. So now the big thing was, now let's cool this down to 50 Kelvin below the transition and see, you know, if we see any difference. And now, you know, obviously what we did was we turned off the light. We did the experiment at 250, then we turn off the light, and then we cool down to 50 Kelvin, we turn back the light, we measure again. And then, you know, to our dismay, it looked the same. I mean, you know, you can see this is left circular polarized light, and this is right circular polarized light. They're about the same, right? Now, there is some modulation here, but it actually has different periodicity, and we understand where that is coming from. That's not it, okay? So initially we were disappointed. We thought, okay, this material is not chiral. But then we remembered that on the original experiment, there were domains, right? And these domains, you can see that they're like 10 nanometer scale, right? Our light, we use a 10 micron light. So you can imagine that these right-handed and left-handed domains, they will be all there and they will cancel out basically, right? So in other words, it could be that the sample is chiral, but then we may have all these domains canceling out. So how do you actually go around this? Well, let me show you a similar example, right? We know about magnetic domains, right? So you can have a ferromagnet and these domains would be pointing on in random directions. Now, what you would do is you would actually put a magnetic field to align these domains, right? That's how you align magnetic domains. Now, you cannot do this with the chiral domains. Chirality doesn't couple to the magnetic field. You cannot align with a magnetic field. So you need something else. So we had this crazy idea to actually align these domains with the light itself. So we did the following experiment. We actually cooled the material in the presence of light. So we first put in left circular polarized light at 250 Kelvin. And while we are cooling the material, we keep the light on. And then when we get to 50 Kelvin, we turn off this light, okay? And then redo the experiment. So here's what you see in that case. So when you cool the sample in the presence of left circular polarized light, you actually see that at 50 Kelvin, there is a very big difference between left circularly polarized light and right circularly polarized light. And as you change the helicity, that goes the right way. Now, after we go to 50 Kelvin, and then now I can warm back up. So as I warm up, okay, so these are higher and higher temperatures, this effect goes away exactly at 200 Kelvin, okay? When the sample becomes normal, that's when the charge density wave state melts, we also lose the chirality. Now, I can repeat the same experiment with right circularly polarized light. I can cool in the presence of right circularly polarized light. I see exactly the same effect, but you can see it's flipped, right? So, you know, here, the left circularly polarized light was lower, it's higher. So what this is saying is that by using left circularly polarized light, I align the left-handed domains. By using right circularly polarized light, I align the right-handed domains, right? It's like putting a field this way and putting a field that way. Okay, so this is, you know, I have only 2 slides left. There's actually, you can think about this, and we had help from our theory colleague, Dicelamide, who said that one way to think about it is the following. So in this system, you know, when you normally cool down, you go from, you know, high temperature state to a phase where you have degenerate left-handed and right-handed domains. But when you shine light, what the light is really doing, it's basically favoring either left-handed domains or right-handed domains. And you can express this in the free energy. And you can come up with a term that actually describes why light with certain you know, polarization should couple to one domain or the other domain. And you know, it kind of makes a lot of sense because we can confirm some of the predictions from this. So I think I'm ready to summarize my talk. I basically gave you 2 examples. In one of them, we were looking at light-induced phase transitions in this charge density wave. And what we saw was that, you know, as you kick with the light, you melt the original charge density wave, weaken the original charge density wave, a new charge density wave that normally doesn't exist in thermal equilibrium came into existence, okay? And then if you waited long enough, it went back. In the other example, I showed you a static case where you're not creating a new phase, but rather you're using circularly polarized light to align domains of charge density waves with left-handed and right-handed chirality. So I think with this, okay, let me skip this. I want to leave you with the picture of my group, and thank you so much for your attention.
Thank you for this very nice, deep, and comprehensive talk. That was a pleasure to listen. Questions, please. Indeed, there is one question in the chat. Have you seen, Hocam?
Let me check. One reason that, okay, so görüntü alın this. Okay, one reason that we use femtosecond pulses is that it provides high temperature resolution, but does it also help that femtosecond pulse have lower thermal penetration because we don't want to alter the material? Thus, using femtosecond pulses allow phase transition without causing further dynamics. It's actually a very good question. Now, you may know that you know, people do eye surgery with femtosecond pulses. The reason being is that, you know, you can control the heat very carefully. You can only damage one area, or you know, and that does come into play when we do light-induced femtosecond light-induced transition. So, for example, right after I kick with the light, initially only the electrons are excited. The electrons absorb the light, and the lattice is still cold. So I can actually realize a very artificial scenario there. I keep the lattice at a cold temperature, but heat up the electrons, right? So in the thermodynamic case, this never happens. Everything, you know, you just wait long enough so that everything comes into equilibrium. And indeed, that is one of the reasons why I could potentially realize new phases that doesn't exist in thermal equilibrium, because I can go into these, you know, very artificial cases where electrons hot, lattice is cold. Yeah, very good question.
Mehmet Hocam, please come.
Sure. Thank you very much for the Very excellent science and very instructive presentation of this complicated subject. So I have two questions. In the transient charge density wave that you presented, which is seeded by the defect, have you seen or worked on the deliberately engineered line defects or similar screw type dislocations?
Yeah, that's a very nice question. So, you know, we haven't, but we did the following. So there are materials that are intentionally chemically doped. So people grow these systems and they intentionally doped chemical dopants, right? Now, and then people did STM on these, and they indeed saw that when there was a chemical dopant, they actually do see this, you know, this dislocation that I was showing. So it's on our agenda, but we haven't done it. So the question, if I repeat the same experiment on these samples, do I see different dynamics? Yes, this is an excellent question, but we haven't really done it in our sample.
Okay, thank you. The next question that I have is, how did you preclude any irreversible phase or structural transition or any defect nucleation in either lanthanum telluride or titanium selenide?
Yeah, so basically everything that I was showing you, all these movies, they are the same movie averaged like 1 million times. So we kind of, you know, redo the same experiment, you know, because many pulses are coming in and we average it, right? And we could also, I mean, it is easy to burn the sample. We can simply, you know, crank up the light intensity and see that at some point, diffraction pattern looks different, like something burned looks like, right? So we know the damage threshold and we stay very much below that damage threshold. So
okay.
There's no long-term change in the diffraction pattern.
Okay, thank you very much, Hocam.
Thank you. Nice to see you.
Nice to see you.
More questions, please. Okay. If there are no more questions, perhaps we can stop here. Nuh Hocam, what do you think?
Thank you. No, it was a pleasure.
That was a pleasure for us and hope to see you in person in nearest future.
I hope so. Yes.
Yeah. Take care of you.
Thank you. Thank you.
Thank you. Thank you.